This ES go to 0, and let me do an example, and I think that's the best way to look at this through an example. Okay, any questions on the general idea that I'm trying to present here? You might go through this at home and think about it a little bit. The idea is that we are trying to look at the input-output relationship, call it an error, and make sure the error goes to 0 as time goes by. We have done the aerodynamics here, and we used the final value theorem to evaluate a number that will tell us if the steady-state error is equal to 0. And I'm claiming that depending on C, A prime, and B, this will not always go to 0 for a step input as time goes to infinity. But here, I'm claiming that it will always go to 0. Okay? And here, meaning that this architecture and that. So let me give you an example, and we can hopefully convince ourselves that it is true what I'm telling you. So let's start maybe here. I have an example here. Consider the following LTI, linear time invariant system. X dot is equal to 0, 1, minus 3, minus 5, x plus 0, 1, u. And y is equal to 1, 0, and x. Design a controller such that the desired characteristic equation is at s squared plus 16s plus 1, 3.1 equals 0. Design a full state feedback controller, let me just say. Full state feedback controller. Okay? So if you do our usual stuff, we will obtain this, s squared plus 5 plus k2s plus 3 plus k1 is equal to 0. And that's the closed loop system. But with full state feedback control. Full state feedback. I mean, although I give you a y, the feedback is x. So we are talking about this, the inner loop. Okay, feedback is x. So this is the inner loop. Okay. Closed loop controller, feedback, gain this. And where did this come from? This comes from Si minus A minus Bk is equal to 0, right? That's how we obtain this. Compare this one with the desired. This is the desired. Compare these two, and you will obtain K1 is equal to 180.1, and K2 is equal to 11. Okay, so this is that. This is the simple stuff. This is what we have done before. Now, the idea is to use now the integral controller to do the same, and you will see that these will change. So let's do the same thing. This is the desired characteristic equation, and that will be example 2. Example 2, solve the same problem to satisfy same requirements, the same requirements basically still have the same desired equation at s squared plus 16s plus 1831 equals 0, comma, but also track x1. And that's why you have y is equal to 1, 0, x, which means y is equal to x1. So we want to track x1. Okay, so it will look like this. The command is x1 is the command plus minus integral ki minus k, and that is your y, and y is equal to x1. So we stabilize the system using that, okay, desired eigenvalues at that, plus we want to track x1. That's the outer loop. Inner loop, stabilize. Outer loop, track x1. Okay? So that's the problem. With 0 steady state error. So track x1 with ES go to 0. Basically no steady state error, and that's why I have the integral over here. We have a few requirements. Desired characteristic equation, we track x1 and ES is equal to 0, which means the steady state error is equal to 0. The problem is find Ki and Ka. K. The feedback gains K and Ki. All right? And that is the problem. This is the open loop. So you have now everything kind of coming together. Open loop, feedback gain, stabilize, and track x1. Okay? This loop here stabilizes the system. This loop here tracks x1. This is what we call the inner loop. And this is what we call the outer loop. Because it is another loop. It's a loop in a loop, right? Two loops. And how does this work in real life? This is my aircraft. And this is still running at about 60 times a second. 60 times a second I will measure, do the inner loop. 60 times a second I will do that. Okay? Inner and outer loop. So, how am I going to find K and Ki? Well, we already wrote down the equation, so this is what I'm going to use in order to find k and ki. So let's write down these equations and try to find k and ki. Okay? So it will look like this. x1, x2, and xn, dot, dot, dot. Right? And xn is here. This here is xn. Okay? So, first thing I'm going to write A. A is here. 0, 1, minus 3, minus 5, that's A. Minus B, 0, 1, times ki. Right? That's the first part. No, times k, I'm sorry, not ki. That's the first part. Second part is B, 0, 1, times ki. And k is, of course, k1, k2. k1, k2. This is ki. C is minus 1, 0. And then everything else will be zeros. xn plus 0, 1 RC. RC in our case is x1c. You might want to write x1c because we're going to track x1. And y is equal to 1, 0, right? And 0. That's that. And this is a 3 by 3 matrix. I don't know if you can see this. This is a 3 by 3 matrix. This A matrix. You see, this one will be a 2 by 2. Right? 2 by 2 here. This is a 2 by 2. Then you have one line over here and two lines over here, 0 and 1 times k1. This is a 2 by 2, and then you have a 0 here. So this will be a 3 by 3. Okay? And maybe you might want to write x1, x2 over here. Okay. So you want to write the characteristic equation for this one. It's a 3 by 3. Write the characteristic equation. It will be kind of long, but I'm going to just write you the result. It's a 3 by 3. You can write the characteristic equation of this one. Characteristic equation. Okay. The characteristic equation of this one will look like this. Because now it's a 3 by 3, it will be S cubed plus 5 plus K2 S squared plus K1 S plus Ki will be equal to 0. That is the characteristic equation of this matrix, of this new system matrix. In fact, maybe we can write this equation down in this matrix. It looks like this, the system matrix. 0, 1, minus 3, 5, minus 0, 0, 0, 1, K2. Zero, I, minus 1, 0, 0. That will be equal to minus K2, 0, Ki minus 1, 0, 0. It will look like that. Okay? And you're finding the characteristic equation of this one. So you'll find the determinant of 0 minus S 0 minus 3 minus K1 5 minus K2 minus S Ki minus 1 0 minus S. Set it equal to 0. And the result is X is plus 5 plus K2 S square plus 3 plus K1 S plus Ki equal to 0. And please try this at home, if you can obtain that. At least this is what I found here. All right, it's basically this one. This is that, this is this, and you find it. So, what do we need to do? Find K1, K2. And Ki. Based on these requirements. So, remember in the previous one, we just equated this one, the desired, to the closed loop. And this was pretty straightforward because I had two unknowns and I had a second order system here and a second order equation here. But here, now the equation is, the desired equation is 61S plus 183.1 equals 0, and this is the desired. Question is, how are we going to match these two? Okay, that's the question now, because you have a second order system and a third order system. The desired one is a second order system, and the other one is a third order system. Why is it a third order system? I mean, the original equation is a second order system. It's a third order because we have an extra state, which is the controller state xn. Do you understand that? Now we have another state, and we have an extra state because of the integral. So previously we had two states, x1 and x2, and that was the LTI, the original LTI. And therefore, the desired characteristic equation is, of course, a second order. But now my total system, this architecture has an extra state that is coming because of the integral. It's a controller state, but it's a state in the system. So you are introducing artificially a new state to the system. Right? This xn is not really part of the actual system. The actual system is here, open loop. It's a second order system. But because of the controller, we have a third order here, a third state. So this is now something that we have introduced, we have introduced a new state to our system, and that is the integral state. It is artificially introduced. We introduced it. It's not part of the system. This is something that we have introduced. Right? And because we have this integral, we have an extra state. We made the problem, we made the second order problem, we turned it into a third order problem. And the reason we turned it is because we have this integral now. But the problem, because it's a second order problem, of course gives me a desired characteristic equation which is second order. The third order, well, that's me. I introduced it. And therefore, I better take care of this one. Okay? So, because now this is a third order system, we will have 3 poles to place, not 2. Here we had 2 poles to place, basically 2 eigenvalues to place. Now we have 3 eigenvalues to place. The original problem tells me these are the eigenvalues here. Okay? And I wonder what the eigenvalues there are. The poles are at, okay, this one has poles. S1 is equal to, S1 and 2 is equal to -8 plus minus 10.9 J. So these are the poles. So basically, system looks like this. The desired characteristic equation, real and imaginary, right? It is at -8 and approximately plus minus 11. So it's here and it's here. This is the desired, these are the desired poles that the problem is telling me. The problem tells me put the poles here and here. And I artificially introduced another pole because of xn dot. And the question is, where should I place the third pole that I introduced, but still satisfy this requirement? Understand? I have now 2 poles coming from the problem, and I need to place a third pole because of xn that I have introduced, but still satisfy this requirement. Where should I put the third one? Should I put it here? Because it's like the observer now. I can put it anywhere I want. Where should I put it? Should I put it here? No, right? It will make the system unstable. Should I put it here? You could. It will make it stable. But who's going to be the one that will die out the latest? These two or this one? It will be this one, right? It will be this one. And you don't want that. Because the problem tells me these two should die out the latest. So if I put it here, this one die out fast, this mode, and this modes will die out a little bit later and will satisfy this requirement. Because this will go away and this one will continue, but this one will die out after this one. So it will not interfere with the requirement. Now this one, of course, during the transient, this one will interfere for sure. But this one will die out faster, and this one will die out at the time that was coming from the requirement. So if you put this one further away, then this will die out a lot faster and will interfere less with the transient as well. Okay? But if you make it very far over here, then you might run into trouble with these gains and other stuff in practical applications, like in the observer. You can put this very far away, but you might run into practical problems. So we want to make it faster than the desired eigenvalue, so let's put it over here, somewhere over here. Okay? So this was the desired characteristic equation, right? The desired characteristic equation looks like maybe here. Let me write it down here. the desired characteristic equation was something like this. Right, it's equivalent to this. This is equal to this. And I'm going to introduce one more root to the system. And I'm going to put it at, let's make it 100. I'm just making this up. Okay? Let's make it minus 100. So that's another root I introduced. The third one will be this. So it will be basically s plus 100. So I put another root at 100 artificially. I introduced it. Times s squared plus 16s plus 1831 equals 0, and this is the one that comes from the requirement. This was the originally desired, and I introduced another one at minus 100. Okay? It could be less, it could be minus 10, minus 50, whatever. And you can try this at home and try different things. So if you do this, if you introduce that, you will have something like this, s cubed plus s squared plus 1783 s plus 18310. This is now the new desired. Okay? This is the new desired, and I introduced a new state, a new pole at 100. So compare this one with that. Now you can find K2, K1, and Ki. I can tell you immediately Ki is 18310, right? This one is equal to that. K1 is equal to 1780. Ki, K2 is 111. I think the numbers came out to be quite large because of this 100s, right? You could make it 10 if you want to. Want to make it 10? It will look like this. If you make this 10, let's place the pole at 10, not at minus 8. We'll place it at 10. Then it will look like this. Okay? It will be s cubed plus 16s squared plus 183s plus 10s squared plus 60s plus 1830 equals 0. It will be s cubed plus 26s squared plus 343s. Is that right? Yes. Plus 1830. In which case, Ki is equal to 18330. K1 is equal to K2 is equal to 21, and K1 is equal to 340. Okay? So this is when I introduce it to at minus 10, right? And look how different there is. There's an order of magnitude difference in the numbers when I reduce it to s plus 10. And what was the original K1 and K2 without the integral control? What did we have? Original numbers were original with no integral control. K1 was equal to 180 and K2 was equal to 11. So without the integral controller, just to stabilize 180 and 11. If you choose the third pole at minus 100, these are the gains. If you choose it at minus 10, these are the gains. And look at K1 and K2. They change every time when I introduce the integral controller. And when I choose the third eigenvalue as a different eigenvalue, they will change. And the original changes as well. So someone had the question, are they decoupled? Which means, can I calculate this K first and then this Ki? Answer is no. Every time I choose another, I add an integral controller and choose another root, K1 and K2 keeps changing. So I have to do that. I cannot do Baskura over here and then do this on top of it. It has to be done together. Because every time I change the requirement for the integral controller, K1 and K2 is changing as well, not only Ki. Understand that? That's an important point. Okay? Good. Finally, before we go, question is, do we finally have zero steady state error? Okay? Do we finally have zero steady state error? So let me do this real quick. It will just take a few minutes to do it. So this is my new A matrix. The A matrix is that. C matrix I just erased. So E steady state is equal to 1 plus C inverse of A prime, inverse of this, and then B. Okay, and B is here. This is B. I'm missing a 0 over here, by the way. This is 0, 0, 1. Okay, so 1 plus C. C is equal to 1, 0, 0. A is this one now. You just have to plug in these K1s and K2s. It will be 0, 1, 0, 1, 7, 8, 3, minus 1, 1, 6, 1, 8, 3, 1, 0, minus 1, 0, 0, over minus 1, 0, 0, 1, and that's B. Okay, this is C. This is A, basically this one of the whole system, and this one is B. You just have to take the inverse of A, okay? And this is B and C. Try this in MATLAB, you will get 0. So the steady state error is equal to 0. Basically, this will go to 0 as time goes to infinity. And this is exactly what we wanted in terms of that. So, as time goes to infinity, the system will track this signal, RC. And RC in this problem will be x1c because c is equal to 1, 0. So, did we accomplish what we wanted? The answer is yes. First of all, we stabilized the system. Secondly, we are tracking x1. And we know that this error will go to 0 as time goes to infinity. That's what we wanted. We are comparing x1 with x1 command. This will go to 0, so that's perfect. At the same time, we stabilize the whole system. The whole system will die out at this requirement. Will die out, will go to steady state at this requirement. And we chose the other one to be faster than this one. So the integral will not interfere with this requirement. So everything is fine now. Desired response is the way it is. We are tracking the system, we are tracking x1, and this goes to 0. Full state feedback over here, tracking of x1 over here, track x1 and do this. Okay? How would this work in practice? Let's say you have a 4x4 like we did for the airplane. This will probably be your next homework. You'll have a 4x4 aircraft. You will stabilize the 4x4 aircraft, but at the same time you might be tracking Q, for example, the angular rate, or the angle, or something else. And you will know exactly how to calculate this and how to calculate that. Is that okay? Any questions? Good, so see you. Yes?
According to which one did you do? Which game according to?
This one, the hundreds. This is, I use this one.
Is there a chance that for minus 100 it will be 0 and for minus 10 it will
Try at home. Try at home. It will not. You know why? Because of this, 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 this. You will always have 0, 0, 1. You will always have 1, 0, 0. And you will always have this minus c, which is a 1, minus 1, 0, 0. Because of these lines, it will always come out to be 0, regardless what you use here. Okay? So, see you next time.